Morning, everyone. So let's get started with today's session. So yesterday we dealt with magnetic force acting on a moving charge particle. And yesterday we dealt with the case when velocity is perpendicular to magnetic field, it will undergo circular motion. There's something similar it's called Lorentz force. Lorentz force, when both electric field as well as magnetic field both are present, both the forces will act. So what would the resultant force? Yes, pretty simply, the resultant force is vector sum of the two. And one very simple and common example of that is something called velocity selector. If there are charged particle having charge q, mass m, velocity v is projected like this, then if it is passes through magnetic field which is perpendicular to the plane of paper shown in the cross form, it will experience the charged particle moving in magnetic field will experience magnetic force. In this particular case, magnetic force will act upwards. What will happen if you make it pass through magnetic field? It will bend upwards. But we can, if we apply electric field also, which is acting in the downward direction, if charge is positive, electrostatic force will act in the downward direction. And for proper combination of all three, it is possible the net force may become zero and particle may go undeviated. Okay, and what is the condition for particle to go undeviated? Net force becomes equal to zero. And so in that case, what has to be value of E? E is equal to, if you write the same equation, E has to be equal to minus V cross B. Okay. So in this case, this particular case, if I take this as X direction, and this is Y direction, and this is perpendicular to this is Z direction. Okay. So in this case, what is the direction of velocity here? In this particular case, direction of velocity, which direction of velocity? Velocity is along I cap direction. Which direction the magnetic field is? Magnetic field is along minus k cap direction. And in that case, electric field applies, means what is the direction of electric field? All are mutually perpendicular. Suppose in this particular case, suppose I add X component of magnetic field. In this, there is already some magnetic field. If we add we add X component of magnetic field, will it have any effect? It will not. So if you add another field in X direction, so in this case, this setup, it is going undeviated. If we add X component of magnetic field, it does not exert any force. So still it will go undeviated. So what does this imply? For particle to go undeviated, electric field must be perpendicular, but magnetic field need not necessarily be perpendicular to velocity. It must have some perpendicular component, but even if it has component along the direction of velocity also, it will go undeviated with same velocity. But if we add X component of electric field, suppose we add X component of electric field also. If we add up electric field in X direction, what will happen? This will start exerting force in X direction. If we add this field, once it was in a state where net force was zero. If we add electric field in the direction of velocity, still the particle will not get deviated, but velocity will not be constant. So there could be some questions on a combination of such fields such that it remains undeviated. For undeviated, what is the condition? For undeviated, velocity it may accelerate or it may deaccelerate, but there's no deviation. In that case, only perpendicular component of forces have to be zero. Okay. We'll come to the, again, we'll take the combination. Before we take combination of such forces, let's first deal with circular motion of a charged particle moving in a magnetic field. And let's take most cases, whenever it has circular motion, it becomes a little easier to understand if we take magnetic field perpendicular to plane of paper, as we have taken in this case. And suppose particle is given this velocity, or particle is given this velocity. Okay, sorry, if particle is given this velocity, it will undergo circular motion. And how do we find which direction it will turn? Very easily, if charge is positive and if the direction of the field, we can find the direction of force which comes along minus j cap direction. Hence, the center also will lie in this direction. It will go undergo circular motion. If the particle is projected at the speed v, and in this particular case, what we have taken? We have taken v to be in which direction? Along X direction. But if same velocity, if we project with the same velocity in any direction in XY plane, will it still have circular motion? So this particular case, what we have done, we have projected along x direction. What happens if you project in some other direction in xy plane? Will it still have circular motion of same radius and time period? Yes or no? Will it have? So earlier case, it was projected along x-axis. Any direction in xy plane. If you project, will it have circular motion? Yes, it will still have circular motion. As long as velocity remains in xy plane, it is perpendicular to magnetic field. And if velocity is perpendicular to magnetic field, it will still have circular motion. Only thing what will happen, center of circular motion will change. And period will remain same. And as it goes circular motion, see here the velocity is v. So here what is the initial velocity projection? I could have written a vi cap. And as it keeps moving from here, it will acquire velocity as it follows this, as it moves in the circular path. Its x component of velocity and y component will keep on changing. Okay, will it ever acquire z component of velocity? It will never acquire z component of velocity. So at different point, it will have x component and y component, but its kinetic energy will remain same. What does it imply? Any instance, if I take, suppose at this particular instance, it has some x component velocity and it has velocity equal to vx I cap plus vy j cap. This velocity, are these quantities related to initial velocity projection? Yes, because the kinetic energy will remain same. It implies vx square plus vy square square root. That speed will be equal to initial speed, and vz will always remain 0 as long as it is magnetic field is perpendicular. So can we find xy coordinate at any point of time? Suppose I ask in this particular case, what is the xy coordinate at time t equal to t by 2? Sorry, t by 4. T by 4, if it moves like this is where it will reach t by 4.
Yes.
This is where it will be at time t by 2. This is where it will be at time 3t by 4. Similar way, if you have to find what is position at t by 6. So t by 6, what will happen starting from here? T by 6 is it will cover 1/6 of the circular motion. So angular displacement will be equal to 60 degree. So from here, where it would move, it will reach at this point here. So this is the point at t by 6. So we can find position at any, we can find its coordinates at any instance of time in terms of capital T. Okay, this part is so far fine. What we have done, keeping this xy component the same. Suppose we add z component. So in addition, so earlier we see as long as it has, if we add z component, what changes happens here? Moment we take z component here, x component and y component will keep on changing, such that their sum of squares will remain constant. XY component will keep on changing. Still, magnetic field is perpendicular to plane of figure, but force is acting only in XY plane. No, for magnetic force does not act in the direction of magnetic field. So force will not have any K component. Hence, it will affect, it will not, so this Vz will not remain affected. Vz, so if a particle has z component velocity, it remains unaffected. So what will the coordinate of the particle at time t is equal to capital T? What will the coordinate of the particle at time t is equal to capital T? So capital T, what would happen? We can split the motion in two parts. What is motion? One is motion in the plane perpendicular to magnetic field, XY plane. XY plane, it will keep having circular motion. But in addition to circular motion, it is also moving along Z direction. It is also moving towards you. So by the time it has completed one full circular motion, it has come back to XY coordinate has become 0. But it has some displacement along what kind of motion?
Z into T.
That direction. Uniform motion. So its coordinate will become, so Z coordinate will be equal to what? Very simple. Since it has uniform velocity, speed into time. That would be Z coordinate. Now something similar we can find. So every time it, and this is what is this, distance is nothing but pitch. So moment we have a component of velocity in the direction of magnetic field, it has motion in plane perpendicular to magnetic field, also along the direction of magnetic field. And that combination is called helical motion. And the displacement it has along the magnetic field by the time it completes one full circular motion, or displacement during the time capital T, this is a term what here written, this is called pitch. Okay, so this is something another way you can understand, and that's what it happens. Now, suppose this is a case here. What happens if you apply a electric field also in K direction?
It will have acceleration in.
So what will happen? So far magnetic field was applying force only in XY plane. Moment we have electric field, it will start applying a force in the Z direction as well. So hence, if there's a force in Z direction, the electric field force or electrostatic force will act in the Z direction. That force will not have any component in XY plane.
Yes, sir.
XY plane motion in XY plane will remain unaffected. So if I apply electric field in the direction, K direction, motion in XY plane, this force will not have any component in XY plane. Hence, motion in XY plane remains unaffected. Only motion which gets affected at XY plane remains unaffected. Only thing what will happen, which will change, only the velocity in Z direction will change. Now, if I apply a field, it will have uniformly accelerated motion in Z direction. So we can apply. So basically what you are saying here, whenever such cases are there, we can split the motion in two parts. Which are the two parts we are splitting into? Motion in the plane perpendicular to magnetic field. If magnetic field is Z direction, motion in XY plane, which will continue to remain circular. And second motion we are taking in the perpendicular direction, Z direction, direction of magnetic field. If only magnetic field is there, it will have uniform motion. If in addition to magnetic field, there's electric field also in Z direction, it will have uniformly accelerated motion in that direction. And we can solve such questions. In addition, what will happen? The kinetic energy also will change. So we look at one question which involves something like this. And this is something what we did with this, something like this. So we look at the path, how the particle will move. In case it has velocity component in the direction of magnetic field as well, this it will have a helical path. So what is the condition for helical path? Velocity must have component perpendicular as well as parallel to magnetic field. Or other way of saying is, if this is the magnetic field, if you want to represent form of a vector, if this is the magnetic field, as long as velocity is perpendicular, it will have circular motion. If velocity is along the magnetic field or opposite to magnetic field, it has straight line motion. But if velocity is something like this, velocity is at an angle to magnetic field, which is neither 0 nor 90 nor 180, in that case, it will have a component perpendicular to magnetic field. It will also have a component parallel to magnetic field. And this kind of combination leads to helical motion. And helical motion, we split into two parts. We split when it has helical motion. This velocity component gives rise to circular motion, and this velocity component gives rise to axial motion or motion along the magnetic field. And in that case of the circular motion, we take this velocity. For calculation of pitch, we take this velocity. So perpendicular component will result in circular motion in plane perpendicular to B. Parallel or anti-parallel component, which is V cos theta, this angle theta being angle between velocity and magnetic field. In that case, it will have uniform circular motion. It will lead to pitch. So axial displacement during the time it completes one full circular motion is called pitch, which is V parallel into T, V cos theta T. Let's take in this case. Suppose this particle, charges plus qm, is projected with the velocity. This is the velocity given. In magnetic field, this is the magnetic field given. What kind of motion it will have if all these three values are non-zero? What kind of motion this particle will have if all three values are non-zero? Shreya, can you tell me what kind of motion this particle will have?
It will have helical motion.
No, so why it will have helical motion? Can you tell me the reason also why it will have helical motion? Because velocity has component perpendicular as well as along the magnetic field. Now from here, can you identify what is perpendicular component which will determine its radius of circular motion? Which is the perpendicular component of velocity?
Vx and Vz.
Vx and v, these two are perpendicular component?
Vy and Vz.
Vy and Vz. Because magnetic field is I cap direction. So it means this becomes my parallel component in the direction. And these two vectors, sum of the two becomes perpendicular component. So if I have to calculate radius of circular path, I'll calculate radius is mv perpendicular by qb. So what will value of v perpendicular I'll substitute here? What is the value of v perpendicular? Vy square plus vz square by qb. And pitch also, how much will be the pitch here? Pitch will be equal to how much?
Vx into t.
Vx into t. And t is equal to 2 pi m by qb. So it's very easy. So helical motion are easy to solve Let's look at, so pretty easy, we can easily do. And if we change the direction of magnetic field, suppose the magnetic field was not I cap, it was J cap. In that case, this component becomes the parallel component. These two become perpendicular component. The moment we know it is all parallel and perpendicular depends on direction of magnetic field. Let's take a case. So in this case, a positive charged particle QM is projected from origin at time t at time 0 with the velocity. This velocity is given. Magnetic field is like this. Okay, so if the question is given, if you have to draw a figure, whenever this kind of motion is involved, it's better to draw a figure such that magnetic field is perpendicular to the plane of figure. Magnetic field is k cap direction. So I've drawn xy plane. And what the velocity? This is the velocity direction. So very clearly, magnitude of velocity is v, and angle it makes is 45 degree. Suppose I ask few questions based on this one by one. And what kind of motion this particle will have, if this is what is given? Can we identify what will be the nature of motion? Anish, what kind of motion this particle will have?
Circular.
The circular motion. Why it is circular motion? First we identify, see, what are the three possible motion? If charged particle moving in a magnetic field, three possibilities are straight line motion, circular motion, helical motion. In this case, if the velocity is perpendicular, dot product of velocity vector and this, it will have circular motion. This is pretty easy, it will have circular motion. Can you also identify the coordinates of center? Can we identify the coordinates of the center of the circular motion? If it has circular motion, it will have some center. So can we identify coordinates of center of the circle? How do we identify coordinates here? Coordinates of center of the circle.
0.
So how do we identify first of all this velocity? And velocity everywhere is tangential. So this velocity vector is tangential to the circle. To identify first of all, the center will always lie on the line perpendicular to this. The center can lie at a distance r on this side, or it can lie at a distance r. What distance r is, I can find value of r. What is the radius? What is the distance of this point from the center? R is equal to mv by q.
mv by qb.
Okay, but only question is, it will lie on the this side or this side. How do we find out which direction the field is acting? Field is plus k cap. So one way of turning would be dot, it will turn right. So force will be towards right. So center will be towards this direction. So what is the coordinate of the center here? The center is at a distance r. Can we find these coordinates of this point now? I
Yes,
can
sir.
easily find them. So coordinates will be equal to coordinates of center r, r by root 2 and minus r by root 2. So those who have problem which direction the force will act, we can also try the direction of force will be in which direction? It will be in direction q v cross b. So if we take v cross b also, you can easily, we take a cross product with k cap, you can easily find I cross j minus j will come in this direction. So we can find the center, coordinates of center. So Anish, have you understood?
Yes, sir.
We have found the center coordinate. Now, if we found the center, can we find the coordinate of the particle at this time here? What would be the coordinates of the particle? We are trying to understand position of a particle. We are trying to focus on position of particle. First, I have taken a simpler case when it is having circular motion, but initial velocity is not along the axis. Can we find coordinates at time t is equal to pi m by qb? What is pi m by qb? We can always express, we know capital T is equal to 2 pi m by qb.
T by 2.
It is basically what is T is equal to T by 2. So what is T by 2 means? Yeah, okay, it is moving in a circular path, but it will be which, where T by 2, where it will be? It will be on the diametrically opposite point.
Yes, sir.
What is the point? It will be from here, it will be diametrically opposite point. At what distance from here? At a distance of 2r. And what angle? 45 degree. Can we find position? We should be able to find position. So this how this particle will move. This particle, whenever the velocity will always be perpendicular to the circular path it will trace out. Only question in which direction is this direction or this direction based on the force. We can find out coordinates also. What will the coordinate? You can easily find out. It will be equal to what? It will multiply by 2. This term, that would be the coordinates of this particle at time t is equal to pi m by qb. Pranav, have you understood?
Yes, sir.
Okay. What happens if we change the velocity? In addition, we have given some velocity in the k direction also. What is the coordinate at the same time? Pranav, can you tell me what will the coordinates at this time now? I'll write the xy coordinate. See, when velocity has k component also, it does not change my xy coordinate at a particular point of time. It will still having an xy perpendicular plane. It will have its motion independent of this velocity here. So this coordinate will be equal to 2r by root 2. And other will be equal to minus 2r by root 2. Only question is, what will be the value of z coordinate here? Pranav, can you tell me what is the z coordinate at this particular point of time is this velocity given to the particle? What change I have made from here? I have added only another component. What is the velocity? What is the velocity you have added here? We have added velocity bk. Can you tell me what will the z coordinate at time t? Pranav? What kind of motion it will have along z axis? Can you define the nature of motion it will have along z axis?
Will it be Vt, sir?
It will be velocity into time. Then this v and time, this we simply substitute. Pretty simple. It will be velocity v into pi m by qb. So as simple as that. So even if it has some velocity also, if it is a helical motion, still we can find coordinates. Not a problem at all. Okay. Let me add something more here. What you have done here, for the previous case, this part is same. You notice any change from previous question? What is the change we find here? Previous question compared to previous question, now there's an additional electric field. In addition to magnetic field, there's also an electric field. So there's a magnetic field like this, B, and there's also an electric field perpendicular to this. Which direction? Perpendicular to the plane. Okay, so if this velocity given, what kind of motion this particle will have? Will it have helical motion now?
No, sir.
So what kind of motion? So if I ask you to define what is the nature of motion it will have in xy plane? What kind of motion this particle will have in xy plane? How would its xy coordinates vary in xy plane? Circular motion.
Circular motion, sir.
It will still, because why it will have circular motion is even if I have added this field here, it does not affect its xy coordinate motion.
Yes, sir.
Why does it not affect? Because this will apply force only in z direction. It will have no component in xy direction. Since it does not have force in xy component, motion in xy plane will remain unaffected. Its coordinates in xy plane. So if I am looking from the top, if I look at the motion, its motion in that plane will remain all exactly the same. Only thing what will happen in addition to motion in xy plane, it will also have motion in z direction. What kind of motion it will have in z direction?
Uniform accelerated motion.
Uniformly accelerated motion. So can we find coordinate at time t is equal to pi m by qb? Okay. XY coordinate will remain same. XY coordinate will not change. What is XY coordinate? As we have seen earlier also. This distance will t by 2. T by 2 it will be diametrically opposite point. So this distance is 2r. This angle is 45 degree. So we know the XY coordinate will remain same. Question is, what will the Z coordinate at this time here?
Half AT square.
So basically we can displacement. Z coordinate is nothing but is equal to displacement along Z axis in time t. What is displacement in time t? Uniformly accelerated motion. There's no velocity, initial velocity. So I'll calculate displacement as is equal to ut plus 1 by 2 az t square. What is az here? What is acceleration in z direction now? Force in z direction. Force in z direction will be equal to q into e by m is the acceleration in z direction into t square. So this is how we can calculate. So we can find coordinate also. I hope you understand what kind of motion. So what will happen here? It will still have a helical kind of motion, but pitch will keep increasing with time. Okay. Find the coordinate will be 0. So a slight change now. If I ask one more question based on this, what is the next question here? Something like this. If velocity is something like this, find time when z coordinate will be 0. Can we find an answer for this question?
Yes, sir.
Okay, let me ask some of you. Bhagishri, can you find an answer for this? If velocity is given like this. Earlier taken velocity like this, there's no z component. Now it has z component also, there's electric field as well. Can you find time? Will it ever have z component? Find time when z coordinate will be 0. Bhagishri, can you think you can find an answer?
Yes, sir.
Tell me how. Don't give me the answer. First, tell me how would you find an answer. First of all, will the z coordinate ever become 0? Which direction it is moving? Suppose I add this z direction. Which direction it is moving? This particle is moving. It is moving along minus z direction. This is given velocity in minus z direction. What has to happen for it to come back to the z equal to 0? Which direction the acceleration must act?
In the opposite.
Opposite direction. So unless if az is positive, then only the particle will come back to the origin, z equal to 0.
Yes, sir.
So is the first thing we need to check, is there acceleration in z direction? Let me check. Why there is acceleration? Which force is acting in z direction? Z force, magnetic force is not acting. Only electrostatic force is acting. So what is the force? What is Az equal to? Az equal to force in z direction by m. What is force in z direction here? Can you mark the force acting in z direction? Is equal to QE by m. That's the acceleration it has, and it's opposite to velocity. Now, can you calculate how much time it will take to come for z coordinate to become 0? What is the time taken? Is similar to kinematic question. How much time does it take for z velocity to become 0? In case of projectile also, when we see, if you just recall, if we project a projectile with velocity v, if acceleration is in the opposite direction, what is the time when it comes back to the same point? 2v by g. Here also we can write what is that equal to? It will be equal to 2vz by az. That's the time it will come back to the origin. Time of flight kind of thing. Exactly same thing we can calculate. What is the other way of calculating? I can calculate z coordinate displacement. I can write ut plus 1 by 2 at square in z direction. If I substitute everything 0 equal to, I can get an answer. I hope you
Yes, sir.
understood. Shravani, have you understood this point?
Yes, sir.
So we are splitting the motion into two parts. Motion in a plane perpendicular to magnetic field and motion in that direction. When we split those two, similar to what we have done in case of two-dimensional projectile motion. Similar way you can solve all such questions involving combination of magnetic field and electric field. Let's look at this question. So I'll give a couple of minutes. All of you try and solve this question now. So let's understand, some of those are clear, some are not clear. Okay, so let's go through that. So what will happen? See, in this case also, if you look at, if you draw a figure, and if I draw a figure in a plane perpendicular to magnetic field, which direction magnetic field is? I cap. So let me take I cap in this direction, let the I cap in this direction. So how is my x, y and z plane will be? This is my y and z plane. Then only right hand screw rule will apply. This is j cap and this is k cap. Let's do a little slowly so that everybody follows. What is given here? And both are acting. Electric field also like this, and magnetic field also is acting in this fashion. So what will happen if electric field was not there? And what is the velocity here? V naught j cap. This is the velocity. So if for a moment, let's similar to previous question, if we forget effect of electric field, because of magnetic field, what would happen? It would have got into circular motion. It would have kept moving in a circular path, something like this. It would have kept moving in the circular path. But now this electric field also is present. So circular path means what? Which velocity? Y and z velocity will keep on changing because of magnetic field. But they will change in such a fashion the kinetic energy will not change. So Vy square plus Vz square will always remain equal to V naught. This part is understood? Tejas, have you understood this part at any instant? Why is this so?
Because
Speed is not changing. Vy square. Now electric field is acting. Now so far we have focused only on the motion in YZ plane. Now let's look at what will happen along I-axis, x-axis. Is there any force acting in the x-axis, Tejas?
Yes, sir. There'll be a force acting.
There's a force acting in the
Yes,
x-axis. So along x-axis, there's an acceleration also. What is the acceleration in x-axis? Force in the x-axis divided by m.
Yes.
And because there's a flow, there's these two velocities. Now, what is this acceleration be equal to? Fx is equal to how much? Due to electrostatic field. That will be equal to q e naught by m.
By m. Yes, sir.
That's the acceleration. So what will happen? What will be the velocity at any time t? Vx at any time t will be equal to how much? Initially, there's no velocity in x direction, ax into t. That will be velocity. So what happened? I understand. So that's the reason. In these two, square of the sum, this will remain same. So what we need to calculate at time t. What will be the kinetic energy at time t? What is given here? Velocity at time t becomes equal to 2v0. It means vx square plus vy square plus vz square is equal to 2v0 whole square. Out of this, these two are equal to how much? v0 square. So it gives you what the value of, sorry, which two? I've marked the wrong one. These two, sum of these two is equal to how much? v0 square. So what does it gives you? It gives you vx square is equal to 3v0 square, or vx is equal to 3 root v0. Now, can I find out the time now?
Yes.
Have you understood properly?
Yes, sir. Now I understand.
Sir, how is it 3v0? 3 root v0? It should be root 3 v0.
Sorry, what I've written. I've written other way around. I put root other way around. 3 root 3 v0. Okay. So we substitute vx here, and we can find the value of time. So what is the value will come? Root 3 v0 is equal to q epsilon v0 by m into t. We get the value of t. Karthike?
Yes, sir.
Have you understood?
Yes, sir.
Anish?
Yes.
Pritam?
Understood.
Clear? Okay. So this
Yes.
something is a combination. So what we were dealing with so far, we were dealing with the combination of magnetic force and electric field, but combination of electric field as well as magnetic field. When both act, we have to take the effect of them together, and we split the motion into two parts. Every time, what are we doing? We are splitting the motion into two parts, one in the plane perpendicular, one. There could be some other combination also. This is a question we had done last time. And quickly, I'll just recap this question. This also is a good question to understand. So previous case, we have taken both magnetic field and power in the same direction. Now what is given? This magnetic field is perpendicular to the plane of figure, and electric field is in the plane of figure like this. And suppose the particle is given a velocity like this. What kind of motion this particle will have? See, if electric field was absent, what kind of motion this particle would have had? Field is present, it would have had a circular motion. But this was the question given. These are the options given. Let's look at this. If there was no electric field, this is the kind of motion it would have had, circular motion. Okay, it would have done right now. But because of electric field, in addition to magnetic force, there's an electric force. Which direction the electric field force will act? Electrostatic force. Electrostatic force every time it is acting in this direction. So because of electrostatic force also, what will happen? It ends up having motion something like this. This is what is given here. And it makes sense that the path will not be circular, it will get elongated, it will become odd shape, we don't know what the shape will be, and comes like this. And since both are conservative, it may have motion like this. And when it comes back here, rather than completing a circle, it may have some odd shape motion like this. And so this is something I hope you understand what the nature of motion is. Now coming back to, so we are trying to understand what is the effect of this field. We understood if field was not there, this would have been the nature of motion. And since the field is acting, it will get extra displacement. Because of acceleration, it will have additional displacement. It takes this shape. So when it comes here, distance is a. Here, this will not be equal to a, it becomes equal to 2a. I hope this part is clear. Tejas, is this clear?
Yes, sir, it's clear.
What kind of motion it will have and why?
It will have a parabolic motion because
it is actually not parabolic. So we will not even call what that motion is, because it will not be parabolic.
Not exactly.
There's a special condition for parabolic. Yeah, I'll tell. Can someone tell me why it will not be parabolic? How do we prove it is not parabolic? Anybody? What is the condition for parabolic motion? For parabolic motion, magnitude, well, basically acceleration has to be constant. That's a parabolic motion. Okay. So in this case, is the acceleration constant? Acceleration due to E is constant, but magnetic force magnitude is constant, but direction is changing. Acceleration is not constant. It will also, if somebody asks the question, will the path be parabolic? No, it is odd shape. We don't know what the shape is, but not parabolic. Parabolic, this is condition which is must. Any motion where acceleration is constant, if velocity is not parallel to acceleration initially, it will invariably has a parabolic motion. Okay, now coming to this question. So basically what will happen here, and when you notice here, this was V, it has become 2V here. Why has this changed? Why V has become 2V? It means kinetic energy has changed. Why the kinetic energy changed? Because magnetic field or magnetic force is not doing any work. If kinetic energy is changed, then some force must have done positive work. Which force has done work? This electrostatic force has done work. So if from here to here, what is the work done by electrostatic force here? From here to it has, if it is, see, you notice easily that electrostatic force will be a constant here. It doesn't depend on velocity. What is electrostatic force? Is equal to QE. If force is constant, so from here it is moving along this path. I can the displacement work, in that case, work done by a constant force is independent of the path. So I could have taken path from initial point to final point, not along this odd path. I could have taken the path as direct path also. Or I can take in any form. I can take the path in, since it's independent, I can take path like this also. So what is the path I've taken from initial point to point? This point, initial point. Why I've taken a path like this? Some part of the path is perpendicular to force and some is along the force. Work done is here to 0. So what is work done? Work done is force into displacement. So what is work done by electrostatic force? Work done by electrostatic force is equal to Fe into 2A. That's work done. How much is that equal to? QE into 2A. That's the work done. And that work done is equal to what? That work is equal to change in kinetic energy. What is change in kinetic energy? 1 by 2m. Final velocity square, initial velocity square. So if I write all those terms, so QE into 2A, thus work done is equal to change in kinetic energy. Final is equal to, becomes 4V square minus V square. That's the condition which is applied here. Second thing is also about casting a rate of work done by electric field. So whenever what is work done, say power or rate of work done, power is equal to F dot product of F dot V. So if in this particular case both are parallel, so it will be F into V. F is equal to Q into V. Here the force is in this direction, velocity is perpendicular direction. So here the rate of work done is 0 at this stage. So that's what this question was. Okay. So these are some questions I will. Okay. This question also is a past mains question. Let's see. Many times we look at the last sentence gives an idea. So a particle having some charge as electron and moving in a circular path of radius of so and so under the influence of magnetic field. So there's magnetic field, and if you apply electric field, it makes it move in a straight path. Okay. So this question is a combination of electric field forces and magnetic field forces, and when it moves in a straight path means both forces cancel out each other. Then find the mass of the particle. So this question is not a too difficult one. This is a part of assignment today. So all of you can try and solve later on. Okay. Let's look at this question. And this question also, whenever questions involve north, south, east, and west, they become a little complicated. So when a proton is released from rest in a room, it starts with the initial acceleration of A naught towards west. Which force must be making it move? It releases from rest and then start with initial acceleration A naught towards west. What does this part of the sentence imply?
Initial acceleration will be due to electric field only.
This acceleration is only due to electric field. Now what has happened? Then it's projected north with the speed of V naught. It moves with the initial acceleration of 3A naught towards west. So why the acceleration has changed? This experiment clearly indicates presence of magnetic field. Because when we change this one, in this case, the force has changed. The force has changed because in addition to electric field forces, magnetic forces also started acting. Find the electric field and maximum possible magnetic field. I think the question was wrong. It should be minimum possible. The maximum possible you can't find. So we'll look at why minimum possible. Okay. So this is what the question is given. Let's see how do we solve. So this question is basically first case. What is happening? First case, only electrostatic force is acting. So V is based on Fe is equal to MA. And what will happen second case when it is given velocity? Two forces acting. In that case, what is two forces acting? Fe plus Fb is equal to A dash. It is based on application of these two things in vector form. So let's see how do we solve that question. So first of all, those who have little difficulty with directions, so whenever north, south, up and down are given, we can assume this as a directions. And if you notice here, I have not taken this direction as x direction. It's easier. We can take east as I cap, J as see right hand screw rule. We have to choose the direction such that all are forming right hand screw rule. North is J cap, upward direction is K cap. Let's try and understand first case. So what has happened? First case, what is given? What is A naught in that first case? Can I write A naught in vector form? So initial acceleration, if I call this A1 and this is A2. What is A1 equal to here? Which direction acceleration is? Towards west. So can I write? It is A naught minus J cap. Let me put in this equation here. What is F equal to QE proton? So Q is, okay, sorry, why QE? I can write as E into capital E. E into E is equal to what? This is force is equal to minus, sorry, mass into acceleration, which is minus E naught J cap. So what is value of E here? We can get the value of E. How much is E? Minus M A naught by E J cap. So that's the direction electric field is acting. Now, second thing we have to find here, magnetic force also acting. So what should I assume as in this case, which direction velocity is given? Velocity is given in this direction. And which direction magnetic force is acting? Magnetic force also is acting in which direction? Magnetic force also is acting along. Since the acceleration is in the west direction, it means magnetic force also acting in the west direction in J cap. So if I have to assume value of B, which component will be absent for B?
J component.
So which component will be absent? See, B is magnetic field is always perpendicular to direction of force. If force is along I direction, it means it will magnetic field will lie only in J and K. It cannot have I component. So B can have only J and K component. Let me assume the B value is B1J plus B2K. This is the value of B. Let me simply substitute the values now. What is Fe? Fe value you already know. What is Fe equal to? Fe is equal to minus M A naught J cap plus FB. What is FB equal to? Q into V cross B. What is V here? V naught which direction? J cap cross of B1 J cap plus B2 K cap is equal to what? Mass into acceleration. What is the acceleration in this case? 3V naught, 3A naught. Which direction? Minus. Sorry, what I have done? Nobody pointed out. Why I written J cap here? This should have been
Yes,
what
sir,
number?
it should be I cap.
Sorry, I cap. So this is something I cap. This mistake. I mean, I don't. This is something simply I cap. So this also. Now from this equation, can we solve this kind of equation? How many? Yeah. From this, is it possible to find B1 and B2? Is it possible to find B1 and B2? You can easily solve, you can find B1 and B2. So this is something left for you. All of you, I hope you have followed what you have done here and find the value of B1 and B2. And this is also part of your assignment today. Complete this question on your own. See that it's properly understood. If not, again, we can discuss that. Only thing what will happen here, we'll see why this minimum thing will come. When we take cross product, what will happen? These two, anyway, 0. So it will not be. B1 can have any possible value. B1 can have any possible value. B1 does not have any effect on magnetic force. Okay. So this part here you can solve and you can get value of B1 and B2. Okay, this question also something similar. All of you can try and solve this question. It's also similar. I think we have done last time. This is also part of today's assignment. All of it should try and solve. Okay, so that is what motion of charged particle in a magnetic field. And then force on a current carrying wire. Current carrying wire becomes simpler, IL cross B. And this was the, I think, step by step, how did we calculate what is the force on a small current element. And then we also calculated if magnetic field is uniform, if magnetic field is uniform, I can replace the longer current element also with an equivalent straight current element. And thus application of this. This we can replace any shape of current element with an equivalent L vector, connecting initial point to the final point. So let's see in this case, we apply in this particular case. First thing what I notice in this case, it is placed in a uniform magnetic field. If it is uniform magnetic field, I can replace any conductor by a equivalent length, resultant length. Okay. Direction perpendicular plane of the figure. Current is flowing. Okay. Okay, so I think this part what is missing, current is flowing in, this is equal to 3 amperes. What is the force acting on the loop? So we don't know, this total current is 3 ampere. We don't know what is I1 and what is I2 and what is I3. Will the force on the loop depend on relative distribution of I1 and I2, I3? Actually, it will not. Why it will not depend on this? Let's look at this. So I3, so we can treat as 3 elements. One element is diagonal. So diagonal element is like this only. What is second element? This part also. So diagonal element has a current I3. Even this element also, these two sides I can replace with an equivalent L vector along the diagonal. So second also becomes again a diagonal, but second one carrying current I2. And third one carrying, and this part also I can replace with an equivalent length, which is again from initial point to the final point. This is carrying I3. So what is the force here? Sorry, this is I1. So this is whole thing is equivalent to length equal to AB and carrying total current I1 plus I2 plus I3. So this is possible only when the field is uniform. I can replace this length with an equivalent length. So magnitude of force is really simple. Okay. This question also had come in the exam last time. This also very simple question. This also part of assignment. All of you can try and solve. Any difficulty we can you can clarify in the work session. And this kind of questions are also common. There are two variants of this question. One question it can ask, it is in a state of equilibrium. Equilibrium also means net force is 0. And typically when we calculate equilibrium here, when the object is in the state of equilibrium, we take summation of forces along inclined plane. If forces along inclined plane is 0, because perpendicular to the plane anyway it becomes 0. And it may also ask sometimes terminal velocity. We have seen some cases terminal velocity. Terminal velocity is a different question. Terminal velocity applies also involves same condition. Net forces have to be 0. Now there are two kinds of question. One case if here B is vertically up. What does B is vertically up mean? If B is vertical, it means force ILB force will be in the horizontal direction. If I draw the free body diagram here, the free body diagram will have something like this. Normal reaction, which is immaterial here. Anyway, they'll always cancel out mg cos theta, and this will be mg sin theta. Which direction the magnetic force has to act? See, if B is vertical, magnetic force will act like this. This will be the value of ILB. This is ILB. Why ILB here? Because the current, length, and all three are mutually perpendicular. You can easily notice the length is in horizontal plane, B is in the vertical plane. So they are mutually perpendicular. So IL cross B will be equal to, actually I should have written ILB into sine of angle between L vector and B vector, which is equal to 90 degree. So this is the free body diagram. I can take its component, and this angle also is theta. So this component we equate, we find the easy, that's the easy one. What happens if B was perpendicular to the plane? Will the answer change if B is perpendicular to the plane? If B is perpendicular to the plane, still it is perpendicular to L. Only thing what will happen, the magnetic field, if B is perpendicular to plane, magnetic field will start acting along the plane. That will be ILB is equal to mg sin theta. So these are two variants here, easy application of this. We have done some question of friction also. In this case, so the question was, as the resistance decreases below 20 ohm, what happens? As the see here, it's like a rheostat. As we keep moving the contact towards this side, the resistance will keep decreasing. As resistance will keep decreasing, current will keep increasing. If current keeps increasing, the force on this wire, since everything is placed in the horizontal plane and magnetic field is in the vertical direction, magnetic force also will act in the horizontal direction. Which direction it will act? So this is the direction of current, I, and this is B direction. So those who are not clear which direction the force will act, actually it is not required to calculate also. The force in the horizontal direction will be equal to ILB here, and if it begins to slide, that has to be equal to mu times N. So this is this kind of question, and what will be N here? Equal to mg. So this question also you can solve, and let's look at this question now. And this question also had come in the test, and this is slightly more challenging question. First, read the question carefully. A semicircular wire of radius r and current I. And this is current I. So this also is I here. Is placed in magnetic field as shown in the figure. On left hand side, this part here has a magnetic field strength of B naught, and the right side has a magnetic field strength of 2B naught. Okay. Both fields are directed inside the page. So this also is a cross field. This also is a cross field. The magnetic force experienced by the wire. How should we solve this question? What we need to find? We need to find the magnetic force acting on the wire. How do we go about finding this magnetic force on the wire?
In the left half, we can take an equivalent length, and
No,
in the
because
right
we
half,
are comfortable. See, this is curved shape is complicated. But curved shape can be replaced with a straight shape only when the field is uniform. The field is uniform in the left part, so we can take the left part. So first part, what we do, we consider left half and right half separately. Why do consider right half separately? So that for each part, the field becomes uniform. Field in each is uniform. One field is uniform, it becomes easy. So what we do then, after the field, after we have done so, what you can do, each part we can replace with a straight wire. So I can replace I can even replace with something like this. Can I replace the left part with something like this? So as you recall, is said we can replace with any shape of the wire as long as starting point and end points are same. I can do it like this also. What is the advantage of doing like this?
One side won't matter.
No, so actually it won't matter. It will matter, but it becomes a little easy. But those who have little difficulty, I can write an ij. So what happens if I take this also I cap, j cap, and field as k minus k cap? Is some people still have this. I'm trying to convert most question into cross product. Because some people have problem with finding right hand thumb rule and all. In that case, it becomes easy. So this part I can write. This is A, B, and C. What is force acting on AB part? It is easy. In that case, it will be I cap cross minus k cap. Is it not? So which direction the force will act? That will be on this direction, force will act in the upward direction. Similarly, which direction the force will act in this element? It will act in j cap cross minus k cap. So that will be along minus I cap direction. Are you all following? So those who have difficulty. So what would this force be equal to? This force will be ILB, and this is a direction. So I into R into B naught. This also equal to I into R into B naught. Similarly, when you look at this part, here what will happen? There also you can do something similar. Again, replace with starting to end point. So I replace this part, something like this is going downwards. If it is going downwards, this force will act in this direction. And this part is going like this. And this is going towards right, against the direction of force will be same. This will be IR into 2B naught. And this also will equal to IR into 2B naught. So I can easily calculate the net force. So this is another way. So last time you can take a straight line also. and then we get root 2r, and then take the components finally. So rather than finding first and taking components, what I have done here, I have taken the length also in component form. As long as if field is uniform, property I have used this, if field is uniform, I can, as long as starting point and end points are same, any shape I can replace it with. So in this case, rather than replacing the state part, I have replaced with two state parts, keeping the endpoint and starting point and endpoint as same. Some of you will find this is a little easier among the two. So this is how we can find, and so finding sum is easy. I hope all are following this. Shreya?
Yes, sir.
Easy?
Yes, sir.
Gayatri?
Yes, sir.
Easy? Well, which method you find easy?
Yes.
You feel that this diagonal is easy, or two state elements are easy? Or nothing is easy?
No, sir. I mean, the diagonal one is easy.
Yeah, fine. Okay. We are comfortable with diagonal one. Good. So some are okay with diagonal, because some people still have problem finding direction. So this is something, if you have direction, you can always use cross product, IJK. Okay. Okay. Then we have magnetic forces between current carrying wire. It's also pretty simple. Why this element will feel force if the current is I1 here? It will feel magnetic force because of field created by other wire. Okay, so whenever I have to find force on this element L, I have to find what is the field here due to second wire. If the distance is D, I can use the formula, we can find field, and I use ILB as the force. Thus the method to find magnetic force between parallel carrying wire. It's pretty simple one. We find ILB. So force on this will be equal to force on this element of wire will be I. All are mutually perpendicular. The field will be dot. So L and B are mutually perpendicular. So straight away I can write magnitude. It will be I into magnetic field created by B at this position. So what is the magnetic field created by B is equal to mu naught I2 by 2 pi D. We substitute and we can find this answer. That's pretty simple. Field at the position of the element. You can find such forces. Okay, and then we have magnetic dipole moment. Any current carrying loop is a magnetic dipole moment. We had revised this recently, not even I think maybe 2 weeks back or so. So all of me easily recall.
Yes, sir.
So any current carrying loop is a magnetic dipole, current into area, and it's a vector. It's direction given by right hand thumb rule. Even a orbiting charge particle also acts as magnetic dipole. The charge particle also is equivalent to a current loop. It's current loop of having current equal to charge into frequency. And based on that, we arrive at a relationship. If a charged particle having mass undergoes orbital motion or circular motion, it is a magnetic dipole, but it also has angular momentum. And we calculate the ratio of the two. We find the ratio between angular magnetic dipole moment and angular momentum is Q by 2m. And this becomes useful for finding magnetic dipole moment for okay, something like this. Now, there are some easy question, calculation of torque. What is the torque acting on a current carrying loop? Current carrying loop, when placed in a uniform field, does not experience any net force, but it experiences torque. What is the torque? Torque is something, how do you find torque? You recall what is the torque equal to? And okay, this is a simple question. Torque is equal to, similar to previous question, M cross B, or MB sine theta. So all you need to do, find the angle between magnetic dipole vector and magnetic field vector. In this case, wherever they lie in the same plane, dipole vector is perpendicular, so angle is 90 degree. And this also part of assignment. You can do this couple of questions, 2-3 questions here, more questions. If not, we can look at this question in the next session also. And there's a torque is this term, and change in potential energy. So torque and potential energy is equal to, what is potential energy equal to? Minus m dot b. And potential energy, what you need to remember, it keeps on increasing. It is equal to negative of cos function, 0 to 90 degree. And this is pretty simple topics, and you can do some questions on this. Maybe this question also we'll discuss in the evening session. Okay, so I think that's what the time we had. So I'll end the session here. So what are some of the questions I mentioned here? Those questions we need to solve on our own.